Udah live, Gus?
Ini lagi setting up di YouTube.
Oke. Selamat malam semua attendees. Kita masih menunggu kehadiran Profesor Ron Harris karena di Utah sekarang masih jam 5:30 pagi ya. Kemarin juga sebenarnya saya sempat ikut acara seminar internasional pembicara dari Amerika. Itu mulainya jam berapa ya? Jam 9 ya, acaranya Teramah ada di sini juga. Nah, sekarang saya bisa merasakan. Soalnya di sana pagi banget ya. Terus karena ini konsepnya yang kita pakai adalah akun Zoom webinar, mungkin terkesan akan satu arah dari pembicara ke attendees, tapi kita di sini nanti akan ada sesi tanya jawab. Nanti pertanyaan bisa langsung ditanyakan di fitur Q&A di bawah. Nanti untuk agar lebih terasa cair dan dua arah, nanti kita berikan kesempatan kepada peserta untuk masuk jadi panelis untuk bertanya langsung dan bisa mengaktifkan kamera dan bertanya langsung kepada Profesor Ron Harris begitu. Sambil nunggu ya. Ghazali untuk aktivasi video panelis
Ya.
mungkin bisa disiapin.
Oke.
Belum bisa juga.
Belum bisa videonya?
Belum. You cannot start your video because the host has stopped it. Terus bilang ya.
Oke. Setting. Dicek Mas, sudah bisa belum? Belum.
Belum.
Ada nggak ada ini ya? Ada pilihannya.
Okay. You turn off my video and wish video preview dialog and hide non-video participants like my video I speak. Stream video setting. Selamat malam, Mas Widi. Terima kasih sudah tanya di chat. Ya, jadi Mas Widi, jadi ini kita pakai Zoom yang tipenya webinar. Jadi memang ada dua tipe peserta. Ada yang panelis, ada yang attendees atau peserta biasa. Nah, nanti yang bisa buka videonya itu yang panelis. Nah, nanti pada sesi tanya jawab kita akan berikan kesempatan buat peserta yang sudah menanyakan untuk kita naikkan ke panelis untuk bertanya langsung kepada Profesor Ron Harris. Begitu, Mas Widi. Ya, malam semuanya. Sambil menunggu Dr. Ron Harris, saya jelaskan sedikit lagi, sekali lagi. Nanti bisa bertanya langsung di fitur Q&A yang ada di bawah, di sampingnya tulisan atau icon partisipan. Itu bisa tanya langsung, nanti penanya terpilih akan kita naikkan sebagai panelis untuk bertanya langsung kepada Dr. Harris. Jadi karena memang konsep Zoom webinar ini lebih satu arah, karena memang kuotanya untuk peserta itu bisa banyak banget, bisa sampai 500. Makanya ini lebih berasa seperti satu arah, tapi nanti di sesi tanya jawab kita akan menaikkan beberapa attendees atau peserta untuk masuk ke dalam panelis untuk bertanya langsung kepada Dr. Harris. Begitu. Terima kasih. Sambil menunggu ya kita. Bisa juga. Saya share ini ya, video salah satu kegiatan riset Dr. Harris di tahun 2019. Jadi Dr. Harris ini salah satu peneliti dari Amerika yang sering datang ke Indonesia. Setiap tahun, biasanya setiap musim panas itu datang sekitar bulan Juli, itu untuk melakukan ekspedisi paleo tsunami. Hal ini sudah dimulai dari 2013. Nah, ini saya akan tayangkan teaser dari kegiatan WAVE 2019. Sebentar ya.
South coast of Java is a real beautiful place. It's right next to this giant trench, this giant subduction zone. And the subduction zone has the potential to produce a major tsunami that would affect this area. It measures the velocity. It's really important that we live there, how intense of shaking they could experience, and how well they need to build their buildings and homes.
after an event, it's easy to get support because you can show how much people are suffering, how much they have suffered, and so people want to give and want to do something to help. It's hard to draw upon that same kind of sympathy or charity when you're doing work up front, when you're doing proactive work instead of reactive work. When people ask you, well, when's the earthquake going to happen? And you can't tell them exactly. And so they're like, well, you know, why should we give it as much attention as we would after an event where we can pull in billions of dollars? And that's the biggest challenge, is getting people to act up front, to be proactive about disaster mitigation.
Ya, videonya singkat ya, cuma 3 menit. Tapi nanti sebelum mulai sesinya Dr. Harris, akan saya putar lagi karena kebetulan beliau juga belum sempat melihat video tersebut. Jadi mungkin sekalian nostalgia waktu riset 2019. Tapi ini sepertinya usulan Mas Widi harus saya oke kan. Karena kalau nunggu-nunggu aja nggak dengerin lagu, boring juga ya Mas ya. Sebentar. Login Spotify. Jadi kempot. Oh, udah datang. Hey Ron. Dr. Harris.
Yes, can you hear me?
Dr. Harris, can you hear me? Yeah, now we can.
Okay. Can you see my screen?
Yes.
Okay, great.
I love your shirt.
Yeah, I'm gonna probably turn my my video off just for bandwidth purposes. Is that okay?
I thought Provo has the fastest internet.
Pardon?
I thought Provo has the fastest internet on Earth.
Oh, probably does. Let's see.
I think we should try to keep video on because we are also live on YouTube. So if you turn your video off, people cannot see you.
Okay.
But if it's not, I mean, like, better without the video on, bandwidth wise, then yes, you can. Hey.
Okay.
Are you ready?
Yeah, I'm ready.
Okay.
You want me to start sharing my screen, or do you want to?
We can just do this first, okay, because I'm going to share the rundown of this event first. I'd like to welcome everyone to this webinar. Thank you for spending your precious Saturday night with us. The committee told me that there were 158 people registered for this webinar. Also, thank you for keep doing social distancing and practicing health protocol. We're not done with COVID-19, and that is why we're doing this seminar online. My name is Hanif Sulaiman, and I will be your moderator today. The rundown for this webinar, the first one will be opening, and then welcoming remark from Prastyadi, an introduction of Professor Ron Harris. Then we'll be followed by watching a short video. And then we'll come to the main event, which is Ron's talk. And there will be Q&A session after his talk. You can type your question on the Q&A feature down below next to the participants. And this question, because we are using Zoom webinar, it might seems like it is a one-way type of webinar, but the selected question will be moved to panelists, and we will allow you to turn your video on and your audio on and ask directly to Dr. Harris and have a discussion. And then there will be closing. So yeah, my name is Hanif Sulaiman. I got my bachelor from UPN and my master from BYU. So I am the right person to be the moderator for today's event. There are some information that I would like to share. This event is part of ICEMIND, which is International Conference on Earth Science, Mineral and Energy. It is the annual international conference, which is held by Faculty of Mineral Technology, UPN Veteran Yogyakarta. This year, FTM UPN Veteran Yogyakarta will hold the third ICEMIND with a theme, Challenges and Opportunities of Mineral and Energy Exploitation and Extraction to Improve Economic Growth. There are 5 sub-themes which will be discussed in this coming third ICEMIND 2020. The first one is disaster management and environmental issues, and then geology, and then geophysics, geomatic and geochemistry, and then mining and metallurgy and engineering. And the last one will be petroleum and geothermal engineering. Please visit our website for more information about ICEMIND at www.icemine.upnyk.ac.id. There will be about 150 papers that will be presented virtually at November 25th, 2020. And there will also be several pre-conferences webinar events, such as this webinar tonight. The webinar which is going to be held tonight is one of the series, and will be presented by Dr. Harris. Before going to the talk, there will be a welcoming remark from Pak Pras Tiadi as the representative of UPN Veteran Yogyakarta. Pak Pras.
Thank you very much, Hanif. Hi, Ron.
Hi.
Apa kabar? Baik?
Baik.
Okay. Yeah, saya baik-baik. Although there's still COVID out there, but yeah, we stay at home mostly.
Yeah.
And we are now in Sabtu sore, yeah, Saturday evening, but you in Saturday morning. So I said, good morning, Ron. Selamat pagi.
Pagi. Selamat malam. Sore malam.
Let's see. Malam
Okay.
already. Yeah. So on behalf of UPN veteran, especially down to Faculty of Technology, Mineral and Department of Geology of UPN, please accept our great gratitude for you, for your kindness to present your invaluable experience in Timor. I think you are the only person so far that still have a great engagement in Timor. And you claim that Timor is your 5th kid, right? So you have 4 kids, and Timor now become your 5th kid, right? So it's like we choose a right person to talk about Timor and Bandar. So yeah, so just give us all your experience about how you dive yourself in Timor and then come up with the result and experience that need for us to be known and benefited for us, as especially we are in UPN for our students. So hopefully among the participants also there are many students, but from the Ghazali, the host of this meeting. There are more than 100 participants of tonight's webinar from you. So once again, thank you very much. Terima kasih banyak untuk your kindness.
Sama-sama.
Yeah, that's all, Hanif. Thank you.
Thank you, Papras. Also, we are also live on YouTube, so the participant here might not be all of the participants. Some people are maybe more comfortable watching us on YouTube, and also don't hesitate to ask questions. If you would like to ask in Indonesian, I will be happy to help to translate. So my first interaction with Dr. Harris was in 2013. He came to UPN before going to Ambon and Banda Neira for his research. Around the time, I also have a project in Masohi, which is very close to Ambon. Then I asked him if I can join him after my project. Some trenches and did some hazard education to school and churches. Then in 2016, I got a scholarship and I went to BU University in Utah. Dr. Harris is my academic grandfather because he was thought process mentor. Then I was mentored by Ron at BYU. Dr. Harris is a doctor in geology who also help people. I always remember his presentation about his turning point in geology when he asked by his friend, "What kind of doctor is your dad?" Then he replied, "He is the kind of doctor that don't help people." Ouch. So Dr. Harris is an expert in mountain building processes, both active and ancient collisional processes, also in hazard and natural disaster mitigation. He compiled historical records of major earthquakes and tsunamis in Indonesia since 1528. He did investigation of tsunami deposits to constrain tsunami inundation models, numerical modeling of and potential tsunami events, construction of tsunami inundation maps for urban coastal areas throughout Java and the Lesser Sunda Islands, also Ambon and Banda Neira. It did also tsunami and earthquake hazard education throughout Indonesia region and Guerrero coast of Mexico. Also some seismic hazard education and disaster mitigation in Utah. He also founded In Harm's Way, a non-profit organization, as a response to the Indian Ocean tsunami of 2004. Messages or like the spirit of In Harm's Way are: the first one is listen to the earth to assess the risk, and then listen to the people to communicate the risk, and help people listen to the earth to reduce the risk. Okay, the next session will be we will watch a short video. Dr. Harris, you haven't watched this one before, so this is a surprise for you. This is a short one. It is probably 3 minutes, so we're gonna watch it.
Pachitan, right next to this giant trench, this giant subduction zone. And subduction has the potential to produce a major tsunami that would affect this area.
It measures the velocity of waves 30 meters down. Kind of gives us an idea of how hard the soil is. And so it's really important that we know where those places are, so we can help the people know there who live there how intense of shaking they could experience and how well they need to build their buildings.
after an event, it's easy to get support because you can show how much people are suffering, how much they have suffered, and so people want to give and want to do something to help. It's hard to draw upon that same kind of sympathy or charity when you're doing work up front, when you're doing proactive work instead of reactive work. And people ask you, well, when's the earth going to happen? And you can't tell them exactly. And so they're like, well, you know, why should we give it as much attention as we would after an event where we can pull in billions of dollars? And that's the biggest challenge, is getting people to act upfront, to be proactive about disaster mitigation.
Okay. That was a teaser from Wave 2019. That was last year. For the next session, it will be Dr. Harris's talk. So Dr. Harris, you can start your talk or presentation.
Okay. All right, can you see my screen?
Yep.
Yeah, yeah, Ron.
Okay. All right, it's a great opportunity for me to be here via Zoom. As Carlos said, a large chunk of my career has involved working in Indonesia, and particularly in Eastern Indonesia, mainly because Eastern Indonesia provides some of the most complete modern natural laboratories for understanding mountain building processes and their effects on people. And the opportunity to merge those two has been a gift of working in Indonesia, mainly because you in other parts of the world, when you go to remote places to study geology, there's not very many people. For example, I've spent years working in Alaska and in Tibet and Himalaya and so on. In Indonesia, you can't go anywhere without greeting wonderfully happy and generous people. And so it's almost impossible to try to just work on the earth without including the people in that process. And so I dedicate this talk to the people of Indonesia, and hopefully what we do today will help all of us to do our part, because disaster mitigation is everybody's problem. It's everybody's issue. So no matter what your expertise, you can contribute, especially those of us in the geosciences, because we understand the hazards better than others and can help to communicate that knowledge, which is what I'd like to do today. So we have established what we call the WAVES Consortium, which involves many academic and government and nonprofit institutions, and which most of them are listed here. I kind of ran out of room. Lately, most of our funding has been provided by Geoscientists Without Borders, mainly because they provide a unique opportunity for those of us like me who want to broaden the scope of our research to include saving lives from natural hazards. And they've been funding our work for the last 3 years. Also, the other funding agencies here are starting from the upper left, BYU, which is my institution, Universitas Pembangunan Nasional, veteran in Jogja, National Science Foundation, the University of Timor-Leste, LIPI, my nonprofit called In Harm's Way. And then we have colleagues from other universities, like the University of Washington and Virginia Tech and Utah Valley University, the Muslim University throughout Indonesia, RISTEC, the BPBD, and the BNPB, and so on. So I appreciate all of those who have contributed. So I'm going to start out by asking a quiz, asking some questions and quizzing you on what you think about arc-continent collision. There still is a lot of misunderstanding about this process. So to give you an example of that, I'd like to start by showing, wait a second, there it is. Start by showing this animation, which comes from a intro geology textbook by Frank Press. He's probably, his book's probably been used by more people than any others. And what you'll see here is a subduction zone. This is an intraoceanic subduction zone. This right here is an ocean continent subduction zone. And here comes a continental margin. It's being pulled into the subduction zone by the negative buoyancy of that plate. And when it starts to get close to the subduction zone, you'll notice that a plate reorganization occurs. Somehow the plate that was pulling it in tears off, and then you reverse the polarity of the subduction. So now the continent becomes the upper plate instead of the lower plate, and you build a fold and thrust belt. So this is still, these ideas were first promulgated back in the late 60s, early 70s, and this still seems to be the state of knowledge of what arc-continent collision is and how it works. It's one of the most fundamental processes in the geosciences because it's arc-continent collisions that actually build continents. So the initial stages of that. So my first question, true or false, is there's three different choices here, three different aspects to this question that I'd like you to ask yourself if this is true or false. When a continent arrives at, should be an interoceanic subduction zone, subduction stops, true or false. The continent continues to subduct, true or false. The arc accretes to the continent and the subduction polarity reverses, true or false. And then number 4, continents are too buoyant to subduct, true or false. The oceanic part of the subducting plate tears away from the continental part, causing uplift by isostatic rebound, true or false. Since arc-continent collisions are fundamental for ophiolite emplacement, I wanted to ask you these two questions, or just this question with these two different answers. First, which best describes an ophiolite, which is a piece of oceanic lithosphere that has been emplaced onto the edge of a continent. Is it a fragment of the upper plate lithosphere that accretes to the lower plate? Or is it a fragment of the subducting oceanic crust that accretes to the upper plate? So I'd like you to think about those questions, and we will revisit them later in this talk. So in order for us to get a better idea as to how to deconstruct our continent collision, we have to use all the tools available to us. And many of these tools have evolved a tremendous amount in the last 2 or 3 decades during the time that I've been working on this problem in the Banda Arc. And you can see here that hopefully your subdiscipline in the geosciences is represented. If not, it should be, because all of geology is needed to bring to bear the story of what happens in our continent collisions. And the original ones that were done were again by people who had been working mostly in inactive mountain systems, in ancient collision zones of the Appalachians and the Caledonides and the Alps. And so these models, as you can see here, of a continent coming in and then the continent clogging the subduction zone and the polarity reverse. So this is in 1970 by Dewey and Bird, and this is Dewey's most recent, even though it's a little bit dated now, attempt to show the same kinds of things. A subduction zone with a continent on it comes in, and you have a plate reorganization that occurs. Somehow the oceanic plate that was pulling the continent in is pulled off of the continent. And then somehow this plate right here then starts to subduct underneath that collision zone. Now, in order for these kind of models to work, there has to be some fundamental assumptions. The first one that's obvious here is that plates are driven by ridge push, because otherwise, how would this plate right here initiate subduction underneath this continental margin unless it was being pushed? Okay. Another one here is that actually, I need to get a different pair of glasses. Could you hold on just a second? My eyes don't work very well in the morning. The second one is that the continents clog the subduction zone, and then the subduction reverses, which is again linked to the first. The third one is that an ophiolite is a fragment of oceanic crust that that comes from the lower plate, as you can see in this reconstruction here. You get this ophiolite in the upper plate because it was scraped off of the lower subducting plate, which means it should have a composition and chemistry or a geochemistry. The geochemistry should show that it comes from a mid-ocean ridge type setting. You can see the same thing here. Another one is that the oceanic slab of the subducting plate, the original subducting plate, tears off, and that tear off then as you can see here, would create isostatic adjustment. I'm assuming you can see my pointer, can you?
Yes, we can. We can see your mouse pointer.
Okay, good.
Yeah.
Yeah, oh, okay, good. That the slab tears off, that there's something that causes that slab tear to occur. And then the last one is that the arc is accreted to the continent, and again, the polarity of subduction reverses, and the continent does not subduct. So the best way, I think, for us to address these questions is to go to places where there's actually arc-continent collisions happening and investigate whether these ideas, which mostly were generated from research on ancient mountain belts where we don't have very clear ideas about what the tectonic settings were and what happened, because much of it has been eroded away or has been overprinted, or we have very few outcrops, but we don't have the original tectonic setting. And so this gives you an example of some modern analogs on the left of an interoceanic arc. For example, this is the Izu-Bonin arc, the Izu-Bonin-Mariana arc in the Western Pacific south of Japan, where we have an old Pacific plate subducting underneath the Philippine Sea plate. And this is the kind of setting that we imagine would exist initially, and then what would be riding on a specific plate would be something like what we see on the right, where we have a passive continental margin. This is the passive continental margin of Western Europe. And you can see that this continental margin is quite complex. It's, first of all, it's not parallel to the, well, parts of it are, but most of it is at different angles to the trench of the subduction zone. And you can see that there's fragments of continent that have pulled off. You can see there's embayments. Excuse me. And little continental fragments and so on. And thinned continental crusts, like what you can see here in pink, and thicker continental crust, which you can see here in gray, and so on. So this would be a good way to imagine that you could begin an arc-continent collision, and it's much more complex than most ancient studies of ancient arc-continent collisions can deconstruct. So this is the outline here of my talk. So essentially, we're going to first look at what is the collisional setting of the band arc continent collision. That's what BACC means. We're going to talk about the evolution of the arc and forearc. We're going to talk about the nature of the continental lower plate, just like we just saw. We're going to ask what happens to that Australian lower plate when it goes into the subduction zone. We're going to ask what happens to the upper plate, which is of Asian affinity. And then what are the risks of the seismic and tsunami hazards that exist in a place where new continental crust is being constructed in this beautiful example of a modern construction zone. So starting with the collisional setting. Most of you in Indonesia are very familiar with this part of the world where we can see the island of Java here with its beautiful, almost regularly spaced stratovolcanoes, which we've all grown to love, but from time to time can create a tremendous amount of death and destruction. For example, here's Tambora right here, which changed the Earth back in 1815. And you can also see Rinjani right here, which caused some problems earlier than that. And Toba is over here in Sumatra. And you have Agung in Bali and so on. These are there because of the fact that the Indian Ocean, right here, the Indian Oceanic Plate, the old and cold Indian Oceanic Plate is subducting underneath the edge of the Sunda continent. And there's three features I want to point out here. First of all, the trench right here, which is about 6,000 meters deep. Some places maybe more, some places less. And then you have the this zone of mountains that are forming here that are still underwater, which represents the accretionary wedge. And then behind that, you have the Forearm Basin, which is a zone of depression because of the weight of the volcanoes and the weight of this mountain belt, both of which are evolving. So this becomes an area of accommodation space for sediments. And you also have this back arc region, which is also submerged. If we look at a cross section through this, this one was drawn by the Earth Observatory in Singapore, you can see those elements I just described, the trench. You can see the accretionary wedge, the Forearm Basin, and the volcanic arc, which is being which is there mainly because of material that's brought down the subduction zone that partially melts here due to the fact that it's got flux melting and decompression melting. This sandbox experiment I'm going to show you here in the bottom part is an illustration of what happens in the secretionary wedge right here. So essentially the way this works is there's a piece of sandpaper which has these two different packages of sand on top of it. The darker sand is a little bit stronger than the lighter sand. The darker sand this represents the edge of the continental margin, which would be right here. The lighter sand represents material which is riding on top of the subducting plate, but is too weak to actually go all the way down the subducting plate. It goes down a little ways, and then you'll see here that it starts to get scraped off. Some of it gets scraped off right at the front of the continental margin and forms a series of imbricate thrust faults. But a deeper layer, which is under more pressure and therefore stronger, can go further down underneath the edge of the margin and start to stack up down here. The process of stacking down here is called underthrusting or duplex thrusting. A duplex is a thrust fault that has a roof thrust and a floor thrust. You can see that these thrust faults here don't have a roof. In this case, it would just be the sea bottom. As a result of the frontal accretion of these imbricate thrust faults here versus the subcretion of these duplex thrust faults here, we've modified the shape of the continental margin. We've actually uplifted it. There's now a thrust fault right here. As this continues, this would the under thrusting would continue to stack up. Let's run it again so you can see it. And it would actually lift that fragment of the upper plate up out of its original position. And that fragment would then be underlain by much lighter material. We're assuming that this fragment here could be a piece of ocean crust in the forearc. This area right here is called the forearc. Or it could be an assortment of different things. But nevertheless, it now has a high angle thrust at the back, which is accommodating the accretion of new material onto the edge of the continent. So to simplify this, if we show these models here, it's like we have a bulldozer, because material is coming in. So you can either think of the Asian plate as moving over the Indian plate, or you can think of the Indian plate as moving under the Asian plate. It doesn't really matter. The same thing happens. You stack up these layers of weak material on top of themselves. And then what the subducting plate also carries with it the volcanic arc to in this case, to the north. So the volcanic arc, excuse me, acts also as a bulldozer and scrapes material up from this back arc region, which again is a place where sediments are being deposited. And then you have addition of rock also in the middle of this through partial melting, as you can see here. So you have this divergent collision zone where we're building mountains here at the front of the plate. We're building mountains here in the middle of the plate by two different processes, magmatic processes and mechanical processes. Okay, now if we turn the other direction and we look at Java and we look eastward now instead of westward, right? We see similar things. We see the oceanic lithosphere here. We see the trench. We see the eastern Sunda arc. We see the forearc. This is the forearc accretionary wedge where material is being scraped off. And essentially the bulldozer moving south. And then if we go way up here, we see on the subducting plate, we see that there's something high standing here. This is the continent of Australia, which is on the lower plate. We can also see small things on the lower plate, like this seamount right here, or this seamount, or this chain of seamounts here. And when these seamounts come in and collide with the upper plate, they indent the upper plate. You can see that this bulldozer essentially has to ride up over that seamount, right? And in the process of doing that, this wedge has to become the angle here, the surface angle of that wedge, we call it the taper angle, has to increase. If you can imagine this bulldozer having to push that wedge of stuff over that mountain, then this would become much steeper. The front would stall and the back would continue to shorten, which would cause it to be a steeper angle here. But once it got over the top of that, you would have just the opposite situation. The really steep front of that wedge of material would then collapse down on the back side. Okay, and you can see indentations here where high standing bathymetric features have come in and created some maybe you can say damage, but you can also see the inboard of these, the forearc basin comes here, and you can see that the forearc basin has been uplifted. Where those seamounts have gone through, we assume that there's been other seamounts in this chain. And you can see that they're causing uplift of the forearc here. Well, if you can imagine the bathymetric feature that the Australian continent presents as it comes into the collision zone, you can see the entire forearc, including the trench. The trench here is like 6,000 meters deep. Right here, it's 3,000 meters deep. Okay, and so this whole thing has to ride up over that continent. And in the process, it lifts all of this area here, which is mostly obscured, up. And then erosion planes it off and allows us to observe what's going on here. This is another view. You can see the volcanic arc. This is the eastern Sunda arc, Java and the Nusa Tenggara Islands. You can see the edge of the continental margin right here. This ocean, this trench is 7,000 meters deep. This trench is 3,000 meters. This ocean here is 5,000, over almost 6,000 meters deep. where the ocean right here in the light blue, just off the coast of Australia, is only 300 meters deep. So this is over a 5-kilometer change in bathymetry. Now, you still see that the plate boundary right here is well defined by what we call, instead of a trench, we call it a trough when it's underlain by continental crust. A trench right here is underlain by oceanic crust. You can see that that in the forearc, where there's no islands here, there are now a bunch of islands popping up, like the island of Sumba and Savu and Rati and Timor and Leti and Moa and Tanimbar, all the way around here to Seram and Ambon. You can see that the volcanic arc is still active, although it looks a little bit different here. This is a volcanic arc that's mounted on continental crust, and most of the volcanoes here are mounted on fragments of previous arcs or on ocean crust. So these are huge volcanoes, and all we're seeing is the very tip of them. So here's the edge of the continent. This is oceanic lithosphere, continental lithosphere. Here's the edge of the Australian continent. You can see how it's gone underneath the upper Asian plate, all the way around here. So now, instead of subduction, we call this collision. So what happens? Well, the best way to find out is to go to these islands and see what the geology says, and to also do geophysical investigations and look at the geochemistry of the rocks and do structural analyses and stratigraphic analyses and on and on and on. That slide I showed you of all the different tools. We can use GPS to try to determine what the pattern of deformation is. We can use analysis of earthquakes and so on. So here in white are the islands, the parts of the forearc which are submerged in the subduction zone that are now sticking up, and are primarily the natural laboratory we will be visiting. I call it the Bandit Range. And someday, hopefully somebody will formally name that range of mountains, but it's a very important range of mountains because it's the youngest mountain range on the planet that's being formed by collisional processes, the initiation of a new collisional mountain belt. Most of these islands have only been on the surface for the last 3 million years or less. For example, the island of Savu has just come up in the last million years, and some of these others as well. And there's going to be new islands that pop up. In fact, there's been a couple big earthquakes here in this part of the Bandit Arc that have formed new islands, although they were eroded away not long after they formed. So how did the Bandit Range rise? What gave rise to it? One of the most important aspects is the convergence of the Australian margin at about 75 millimeters per year, which is a fairly fast rate into this zone of convergence. The Australian passive margin just means that this margin developed a long ways away from a plate boundary. And so there's essentially no deformation of the sediments that have been deposited on this margin until they arrive at this trench. Here's the Banda volcanic arc. Another thing that's really interesting is that the orientation of this collision zone here is oblique to the orientation of the Australian continental margin. So the collision is not simultaneous all the way along this. In fact, if we pull the Australian margin back, you can see it first bumped in to the Bandit Arc right here in Timor and in Suriname. And since then, it's been migrating to the west and to the east from that point. So the collision becomes younger and younger and younger in this direction until you get to a point where it's initiating right here south of the island of Sumba. The velocity of the collisional propagation is about 110 kilometers per million year. Now, if the continental margin of Australia was completely smooth, like we always assume, right? Then that would be a smooth propagation of the collision, but it's actually not. The northern margin of Australia is very irregular, just like the slide I showed of the western margin of Europe. And so it's not as smooth. You can see that Sumba is a lot larger than Savu. Timor is a lot larger than these other places. And so generally it propagates this direction at 110 kilometers per million year, but there are promontories and there are recesses. So you can see here, this is like a zipper, as I show in this drawing here, that the Australian continent is being pulled into the subduction zone, just like if you were zipping this up in a collision zone. So if we slice through the collisional zone here with a series of serial sections, this is kind of what it looks like. So the black would represent the Asian plate, and the gray would represent the Australian plate. The yellow would represent parts of the Australian plate which are accreted to the edge of the Asian plate, just like I showed in that animation. And this shows the progression of collision from the island of Savu, which is right here, all the way to Timor. You can also see there's some red, which is intruding into the black. That's the active volcanic arc. And so if I've arranged these sections so that the active volcanic arc is all in the same place, right? Because everything else in here is moving. And even the active volcanic arc in this last stage is moving. When you study ancient collisions, you actually start with this right up here. And you do all of the investigative work you can, and then you try to deconstruct the rest of this, like take it apart, the opposite of what an architect does, right? But the nice thing about the obliquity of this collision is that each one of these is actually a snapshot. So if we want to know what Timor, the central part of Timor, the part that's collided the most, looked like when it started, we don't have to deconstruct it. We can actually travel over here to Savu, and we can look and see what it was like, assuming that the lower plate and the upper plate are similar over that 500 to 600 kilometer distance, which in most cases they are. There's obviously some heterogeneities. So the Bandit Range is the consequence of this collision. So let's look at, and first of all, look and see what's coming into this collision zone. This is a seismic image from CGG in Australia that shows the Scott Plateau. The Scott Plateau is this area right here. And a plateau means that it's not the shelf. The shelf is here. It's not actually the abyssal seafloor. It's actually somewhere in between. It's a part of the continental margin where the continental crust has been stretched and thinned. So it doesn't have the full thickness that it does here. And the Scott Plateau has essentially three different parts to it. first of all, this lowest part down here represents the basement of Australia, which is, Precambrian in age, over 1 billion years old. On top of that, unconformably, are some sedimentary rocks which formed in a basin when the Australian continent was actually part of Gondwana, meaning that the northern edge of Australia right here was connected to India and some other strands of continental crust, which has since rifted off, forming this passive margin. When the rift occurred, the basin was uplifted and eroded partially. And so there's this unconformity here, which is shown in blue. And you can see that most of these faults, which are associated with the rifting, stop at that unconformity. And then a whole new set of units was deposited on top of the continental margin, and we call these the Australian passive margin sequence, because this was an intercratonic basin, it wasn't a passive margin. So essentially we have the pre-rift Australian basement and its cover sequences. We have conformity, and then we have the passive margin sequences. So all three of these are different. And here's the abrupt edge right here. You can see that the passive margin sequence thins in this direction because most of its sediments are coming from the continent. And so the further you get out here, the less of those there are. So we call this the continental rise, the continental slope, and the continental shelf. This is what's coming into the trench. The good thing about going to a modern analog is that you can see right here what the lower plate passive margin is like before it collides. Right here, we can't see that anymore because it's gone down into the trench to form this trough. And now these have been highly deformed. And so it's hard for us to just look at this and reconstruct what is here. So we can look at the original construction of the upper plate and the original construction of the lower plate and follow them right into the collision and then see what happens progressively through time, the more convergence there is. So what I want to do here is show how the stratigraphic units in the collision zone, this is what the passive margin looks like when it's gone into the collision zone. It's all stacked on itself and very similar to the sandbox model I showed you. Right, here's the actual point of collision. Here's the passive margin going in. The blue represents the passive margin sequence. The yellow and red and orange represent the pre-rift, which was part of the Gondwana intercratonic basin. And then you have basement underneath that. There's one very important unit that's in this continental margin, which controls to a large extent how things happen once they go into the trench. It's a early Jurassic to mid Triassic unit called the Wailulu Formation in Timor. And it's right here at the base of it's below the passive margin sequence. It forms the top of the Gondwana sequence. The reason it's so important is because it's a unit it's hard to know what the original thickness is, but here on the passive margin, it can vary, as you can see here, depending on the structure, from a few hundred meters thick to over 1,000 meters thick. And it's made up of mudstone, meaning that the clays that are inside the mudstone many of them are still expandable. So they haven't been buried deep enough to actually transition to illite. So many a lot of the clay minerals in the Wailulu are still smectite rich, which means they're extremely weak. And they also have the capacity to carry a lot of water with them in their lattice, in their mineral structure. And so essentially what you've got here is a layer, a water-rich layer underneath the blue, which provides a glide plane. If you're going to start squishing this, then what's going to happen is that the blue is going to detach from the underlying units because of that zone of essentially slurry. When the Australian oil and gas explorers drill into that, the water there is under so much pressure that it commonly blows out their wells. The amount of pore fluid pressure increases dramatically there, almost to the point where it's completely supporting the blue layer there. You can see that when these two different units come in here, I've tried to color this the same as this, that the blue unit scrapes off and is frontally accreted. And you can see the accretionary wedge right here. You can see how complex. It's hard to get a good image using seismic reflection here of this, because these formations are now broken and complexly deformed, meaning that they are rotated in various directions, both vertically and horizontally, and they're also being broken by brittle processes. So essentially, you can correlate the units that are on the passive margin here very well with the units that we see in the actual accretionary wedge. There are some units that we find in this that we don't find over here, and some of that might be because of the fact that this continental margin stretched out much further than what we're seeing from the current margin, meaning there could have been blocks that were continental blocks or seamounts or things that were out in front of the continental margin that were the first things to be accreted. And we think we see some of that here in Timor. Okay, just to summarize then, these are the most important factors here. Okay, so let's look at some C-beam work, sonar and other processes to try to image the seafloor where this collision starts. So this is the island of Sumba right here. So this is the subduction zone. And where the Australian continental margin, the rise part, the most distal part of the continental margin starts to go into the subduction zone, you can imagine that you now have increased the influx of potentially accreted material by an order of magnitude. The material riding on the eastern part of the Indian Ocean is not very thick. So the accretionary wedge, even though it's there, is not very large. But now that you're bringing this continental margin in, where you have this 3,000 to 4,000 meter thick wedge of sediments, which thickens towards the shelf. So the more it goes in there, the thicker it gets. You have a interesting situation where initially the taper of the wedge, which here is about 5 degrees, right, thins dramatically here to about 2 degrees, which means that this wedge has met something which is not as strong. So if you're bulldozing material over something rough, then the slope of the material is going to be steep. But let's say you bulldoze that material over some wet mud, a slurry of wet mud, then it's not going to be as steep because there's not going to be as much friction at the front. So the front is going to collapse downward, which is what we see here. These black blobs here are actually intrusions of that mud from the Jurassic and Triassic up through the accretionary wedge to form this zone of diaprism. We can't even actually track the frontal thrust of the accretionary wedge any further to the east than right here, because what it becomes is this diffuse zone of mud diaprism. This map is by Masson et al. Nancy Breen also did a similar survey, which, if I go back here, is just this area that's boxed here. So a little bit more detail. Here's the oceanic plate subducting underneath the Asian plate, but then you can see that this zone of deformation, which she's outlined here, okay, all of the material that she could see that was resurfacing this submarine wedge, you can see it's getting wider and wider in this direction. You can actually see some of these mud ridges. They're not just circular diapirs, they're actually ridges where, if you look at this cross section, the seismic line through here, you can see the TF means the frontal the thrust front of the accretionary wedge. So this is all being thrust on top of itself and being deformed. But out in front of that actually are these mud ridges. You can see each one of these red intrusions are coming from the Wailulu Formation. As it's starting to go down, the pressure is increasing, just like what happens when a well penetrates it and it blows up. What happened here is the pressure got so great that the mud shoots up through the upper layers and erupts on the surface. And so we think this is showing us how these thrust faults actually work. The next thrust is going to step out and go right up through that mud ridge. And then this part of the lower plate will then be accreted. So the thrust front will then be here. The next one will then go here and here. And the next one will go way out there. And so these little packets of the lower plate, essentially the passive margin sequence, are being accreted bit by bit, but they're being processed before they're being accreted by the movement of this very weak Wailulu Formation. Notice that here, this material keeps going down, just like in our sandbox experiment. It keeps going down. It can't go all the way down. It's not strong enough to go all the way down into the mantle. So what happens to it is it gets accreted further to the north. If we look at some other seismic lines across this, these are again published by Martinez Duran et al. And you can see here, this is the passive margin sequence right here, coming in to the collision zone. And you can see that the stresses that are being caused by the collision are either reactivating existing faults or causing new faults to occur on the oceanic plate. So you can get earthquakes out here, and we'll see some in just a minute. Here's what happens further to the north in the accretionary wedge. So here's the deformation front right here, and you can see these beautiful examples of folded and thrust rocks, both fault bend folds and fault propagation folds that are accreting this passive margin sequence. Some of the thrusts are huge, some are thinner, probably because of the way that the mud diaprism pre-process the accreting material. You can see here, these are highly vertically exaggerated, so these thrust faults are not nearly that steep. I just want you to know. Okay, so if we go back to our serial sections, you've now seen what's going on to form this blue area here, which is the frontally accreted material that's being accreted to the edge of Asia. And we're also going to look at some of the material that's in this yellow part, which is the pre-rift Gondwana sequence. This sandbox model was constructed to show two things. First of all, it's to show how this material that's coming in can be delaminated, meaning that part of the material will stack up in one place and another part of the material will stack up in another. And then it's also going to show what happens to a very strong upper plate. So this is a piece of plasticine clay, and these are layers of lime and of sand, the lime being not as strong as the sand, which is very similar. It's scaled to the same thicknesses and strengths as we see in the Bandit arc. So initially, you can see material frontally accreting to the upper plate. So the black would represent the Asian plate. All this other stuff would represent the Australian passive margin coming in. So here's these thrust faults. You can also see the material goes underneath the edge of the Asian plate and starts to stack up under here to become a subcretionary duplex system. And look how it's deforming the Asian plate. It's folding it back towards the north. So not only are all of these thrusts verging or moving southward relative to the stuff underneath them, this area of the collision zone is moving northward. Just like I showed in Java, there's bivergence northward and southward. Now, look at how this has been deformed, almost vertical. What we think has happened in the Bandit arc is that piece of the edge of the Asian plate actually detached from the rest of the Asian plate, right? You can see here, and you can see how it was folded into a similar shape as this, and then carried back up over its roots, and eventually completely buries the forearc region. This is one of the big conundrums of the Bandit arc continent collision as to what happens. This is, I'm only showing here the forearc crust, but there's mantle down here. So this is a large piece of lithosphere, right? It gets overridden by the material that's stacking on top. But where is that? Does it go all the way out to here? And is it like splitting the continent up? Or what happens to that? Right here we have the volcanic arc, 30 kilometers away from material accreted from the Australian margin, and the entire forearc is missing there. It's 3 kilometers deep and 30 kilometers wide. We see this kind of feature in many arc continent collisions in ancient times, and this has always been a mystery as to what happens to the forearcs. Okay, so let's talk about the evolution of the forearc. Again, here's the amount of Australian continental crust, which has underthrust the Asian plate. There's the trough. And the first island that pokes up is Sumba Island. And if we go to Sumba Island, this is some work done recently by, actually, I can't read that word. Whoever that person is, they did some great work. Published in 2018. First, I wanted to make you aware of this line right here. You can see it changes colors. It's dark blue, starts to get a little bit green, goes to yellow and red, and then goes back to green and blue again. This is one terrace of coral. It represents a single location of sea level at a time. I think 125,000 years ago. So you can see that here, it hasn't been uplifted very far, but over here, where it's a long ways away from the coast, it's been uplifted much more. So the uplift rate here is higher. So the change in colors represents the uplift rate. You can see here it's scaled so that the red is showing the highest uplift rates and the blue are showing the lowest. So something is causing this part of Sumba to really go up much faster than the sides. But if you do the structural geology like Fleury and others have done, you can see that most of the structure here is from normal faulting. You can see that this whole thing is collapsing back down, right? These colors just show elevation, but as they collapse back down, they actually expose the rocks that are the deepest here in Sumba Island. So we call this extensional exhumation. And you can see those rocks exposed right here and in several different places right there. Well, what are these rocks? This is a diagram by Fleury showing the uplift on this part of the island. Again, this blue line is one strand of sea level. You can see another one right here, but you can also see that they're far away from the coast, but as you go this direction, they get closer and closer and closer to the coast, which means that the uplift decreases to the south. You can see the composition of Sumba is, it has a basement made up of igneous and metamorphic rocks. And also it has a cover sequence of sediments that make up that forearc basin. And so this provides a great view of what's happened in the eastern part of the Sunda Arc before the collision, and then what's happening during the collision. I know this is really messy. These are three strat columns from East Sumba, Central Sumba, and West Sumba, but what I want to draw your attention to are these intrusions of igneous rocks and volcanic rocks. You can see that this has had a prehistory and the ages. So you can see the ages of the modern volcanic arc here, maximum 15 million years old, but most of them are much younger. We don't see anything older than that, right? But if you look at the volcanic rocks in Sumba and the plutonic rocks in Sumba, you get ages of in the 80s and 90s and 40s and 50s, right? This is a volcanic arc that predates all of these, right? There was something going on here that's now in the forearc, underlying that forearc basin that we don't see in Java, but because of the Australian margin has slid under here and lifted this up, we get to see the actual composition, structure, and age of the forearc basin, the forearc basement. A very rare thing to be able to do in any subduction zone. So how did that, basement get uplifted? Again, it has to be because of the underplating of the Australian margin. This shows the underplating. You can see that the Australian margin material is shown here in yellow, and you can see how it goes underneath. And here I've shown it in red because it becomes metamorphosed. You can see here the metamorphic part of it. So there's now metamorphic rocks on the lower plate and the upper plate, right? And you can see those metamorphic rocks exposed really well in this part of the collision zone. And I also show on here the pattern of uplift that we get from the coral reefs, that as soon as these islands start to get close to sea level, they start to grow a coral, but they continue to be uplifted, right? And so the coral, which initially is just a really small area on the peaks of this young Bandit range, as the peaks rise faster than they can erode, the coral terraces keep growing out on the edges of them. So the oldest coral is in the middle and the youngest coral is on the edges. I know this is different than what Darwin showed. Darwin's atolls, right, grew upward as the oceanic plate that the seamount was on was sinking, and so the coral tried to keep up with the subsidence rate, and eventually couldn't, and became a guyot. But in this case, what's going on is that instead of subsiding, we have uplift, and so the coral terraces ring these islands, every one of them. And because a terrace represents an ancient horizontal, then any kind of, it provides a way for us to detect any kind of warping that is going on due to deformations over a very short period of time. Most of these coral terraces range, I mean, the youngest ones are Holocene, which is less than 10,000 years old, but they range in age to over 1 million years. So they provide a unique window of opportunity for us to detect the deformation pattern. And look at it here. So this is a coral reef here that was horizontal, but now it's tilted back to the south. And the uplifted reefs are here on the north side of Savu. The island of Roti is just the opposite. The south side of the island of Roti is coming up faster than the north side. The same is true in the westernmost part of Timor. The south side is coming up faster than the north side. And then you get to East Timor, and the north side is coming up faster than the south side again. So these patterns are telling us something very, very important about how the collision evolves. If we go to the northern part of these islands, we can see pieces of the Bandit Terrain exposed. We can see it exposed. We can't see it exposed in Roti, but we can see it, well, it's been drilled into on the north coast of Savu, and you can see it exposed on the north coast of Timor. And just like this model here, where it deformed the Bandit Terrain here into this huge north verging anticline with vertical limb here. You can see that same thing if you go to the north coast of Timor. Here's the vertical limb right here. These are volcanic rocks from the Savu Sea, only 3 million years old. And they've been folded up, and where they turn around right up here has been eroded off. But we're looking essentially at this part right here where they're vertical, or this part right here. If you continue to go to the south, you can see large chunks like this. These are high-grade metamorphic rocks, which have ages, between 39 and 33 million years old, and then nothing happened to them since then. So there was something going on before the current Eastern Sunda Banda arc, which we have fragments of that are in the forearc here. They're obviously not pieces of Australian basement because of their ages and their compositions. Sediments that overlie them have affinities that are Asian. Right at the base of these, you can see in the foreground here, and at the base of this big clipping of the Bandit Terrain, is melange, very thick melange. And surprise, surprise, most of the matrix of that is Jurassic and late Triassic mud from the Wailulu Formation, with blocks of other stuff, Triassic sandstones and other things. If you get, so here this used to be the subduction zone right here. This was the upper plate, and here's the Australian lower plate. As it came in, this is material that was under thrust. So this is the roof thrust right here. And there are thrusts down here that you can see. This is the floor thrust, and this is the roof thrust. The green is the melange. And you're essentially looking at these big blocks like that there. You can see pieces of limestone here, which are protecting the really smectitic rich mud from eroding away underneath it. So this whole thing is just made up of a mixture of blocks from the upper plate and the lower plate. this is how we know that these pieces of metamorphic rock, which some people have interpreted as Australian basement, we know that these are not from Australia, and that they had a prehistory. They're actually parts of what we call the Great Indonesian Arc. Actually, let me go back for a second here. So if we look at the island of Timor and the island of Sabu and Rote here, you can see that they actually are made up of these four elements. First of all, the volcanic arc, which is right there, is one element. This is the Forearm Basin. And the Forearm Basin is uplifted here, right at the edge, like you can see here. And that black unit right there is the Bandit Terrain, is what we call it. We call it the Bandit Terrain because it originated north of what are now the Banda Basins. And as the Banda Basins opened, they moved this material southward. I'll show you how that works in just a second. You can see that the yellow is the stuff that went underneath the Bandit Terrain and accreted. I show you this gradient of color here that corresponds with grade of metamorphism. Because these went deeper into the trench and were subjected to higher pressures and temperatures, they're metamorphosed where these aren't. And then we have the blue, which represents the post-drift stuff, which is above the Jurassic Wailulu Formation. Okay, let's look at what the Bandit Terrain looks like in Timor. Now, I showed you that initially it was probably this big thrust sheet that covered most of that yellow, right? But it's been eroded back. And so we only see the northernmost part of it. There's some blocks like in East Timor that have been penetrated by wells offshore, okay? Because most of the uplift was here along this choke point of the subduction zone. So you can see some of those blocks that are buried under these basins here, right? Which have been penetrated by wells. But look at this, look at these ages here. So we've done about as much geochronology as we can possibly think of on the Bandit Terrain. There's now some new methods that we can use, but we've looked at the argon ages of micas and hornblende. We've looked at the ages of garnets. We've looked at the rubidium strontium age. We've looked at the fission track ages, and this is what they show: that these black things have come from the Asian margin and are not part of the Australian basement. So where did these things come from? Well, if you look at this, you can see that this is my reconstruction of the Bandit Terrain back at 30 million years ago. And you had essentially the Great Indonesian Arc, which came through here like this. So that's where it came through Sumatra and Java and then turned kind of to the north like that. And then you had the opening of the Celebes Sea, which separated material from this part of the arc to that part of the arc, which is the northern arm now of Sulawesi, right there. And here's the central part of Sulawesi here. And then you had this subduction zone continue to roll back, and it pulled the Great Indonesian Arc apart again, right here, sending this part to the south, which then became the Banda Arc, right? Later, the foundation of the Banda Arc. And then at 10 million years, you opened up the Banda Sea, which is here in green. And now you have fragments that used to be connected to Sundaland, which are now in the forearc of the Banda Arc. This is accomplished by this process we call slab rollback. This is a reconstruction I show of essentially what is one way in which you can initiate subduction in an intraoceanic setting. You have two different ages of lithosphere that are juxtaposed by a strike soot fault. This is older than this one, so it has more negative buoyancy and can sink just from its own weight. And as it does so, it changes everything. Okay. because as it sinks, it's going to sink from here all the way back to there. Well, if this plate can't move like the Asian plate, usually doesn't move very much at all, then you have to open up a new ocean basin above this. What it does is it actually tears the arc apart. So the arc that was here is the weakest part of this upper plate, right? Because it's thermally weakened by the magnetism. And so as soon as you start to roll this back, you open up a new ocean basin, a spreading ridge and so on, but it's above a subduction zone. We call this a super subduction zone ocean basin. It has the structure of oceanic crust, but it has the chemistry of arc-related rocks and back arc-related rocks. So you can now see the arc here, and here comes the continent in to collide with this. So essentially the Bandit arc is built on a piece of the great Indonesian arc, right, which was rifted off the edge of Sundaland initially. These are some of the ocean basins that have opened in the Indonesian region. The blue are the oldest, like the Philippine Sea Plate here. This is the oldest part of the Philippine Sea Plate. This Philippine Sea Plate is one continuous back arc basin that opened here, then opened here, then opened, is currently opening here, right? You can see the same thing occurred here. As this Pacific plate or the Indian plate that was subducting along this edge was rolling back, it was tearing fragments of the Asian plate off. For example, you can see these fragments here that tore off this edge of Asia to open the South China Sea. And then we see these fragments here in northern Sulawesi, which were torn there, and then to open up the Saliba Sea, and then so on, all the way down to here. The color represents the age, 0 to 10. I'm having a hard time reading that. So if we zoom into the Bandit arc, you can see that the Bandit arc occurred by opening the North Bandit Basin first. So these blue rocks here are arc terrains, arc and forearc terrains. They make up the Lucipyro Islands and other islands that are fragmented. If you look at the South China Sea, look at all these fragments in the South China Sea of the Asian margin. This is a similar thing, but except these are arc terrains, right? And then you opened up the South Banda Basin, which pulled more of those terrains further to the south, and the current Banda volcanic arc is mounted on many of those. And so the forearc of the current Banda arc is made up of these blue terrains. It's made up of fragments of an ancient arc that's now thrust up over Timor, which I show here. It creates Sumba, and it creates the northern part of Savu and Rate, okay? One of the best examples of this process is shown here, where you have the Philippine Sea Plate. For example, you can see these places where there were remnant arcs. So this is where the volcanic arc used to be, and then the Paleoverse Basin opened up and tore half of that arc over here. So the arc was then active here, and then it opened up again, right? So there's the arc, and then it opened up again to make the Mariana Basin here, and here's the active volcanic arc. So the similar thing occurred just to the southwest of where this is. Okay, how much time do we have? Are we done?
We are scheduled to end it at 8:30, which is like 13 minutes from now.
Okay. So let me just finish on the Bandit collision stuff, and I'll mention quickly what we've done with the disaster mitigation stuff. So to summarize, here's the Australian continental margin, in which you can see is very irregularly shaped. The reason we know that is because Sumba right here is being uplifted so fast, but this part of the Bandit arc isn't, it's only been uplifted really recently in Savu. Okay, so there's this prong sticks out. So it could be a prong, or it could just be an individual like piece of continental crust which is detached from this. We don't know exactly. but something is out there further away than the normal Scott Plateau. So this is 6 million years. It comes 6 million, about 6 to 8 is when it first contacts here, thanks to some work done by David Haig and his group on the sedimentology, and some work that we've done on the metamorphism. The metamorphic ages of this lower plate are about 8 million years old. And you can see kind of how this irregularly starts to form the island of Timor here. That's when we start to get turbidites shed from the island. About 4 million years before that, the forearc is just covered in calci-lutite, and then it gets covered with the first turbidites. As we continue, we start to get uplifted terraces that we can now date, and you can see those are happening in Sumba. Sava really hasn't come up yet, and now the present here. And so, you know, the youngest age of the accreted continental rocks are between 5 and 8 million years old. The metamorphic cooling ages are about that same age. The volcanic arc, you can see it just keeps going, right? Some people say the volcanic arc is supposed to shut off during an arc continent collision and the polarity is supposed to reverse, but that didn't happen here, right? The volcanic arc is still going. In fact, in this part right here, where Wetar and Alor have gone extinct only in the last million years, there's an active volcano to the north of that called Gunung Api, which is still going. It just means that the volcanic arc is shifted northward because of the low angle of subduction of the continental margin. Island emergence timing, we can get that from the forearms and from the coral reefs. And so let me just summarize this new work, finish the arc continent collision part by showing this new work here that's been done using seismic tomography from Megan Miller and her group at ANU. So the blue is showing places where seismic waves go fast. The red is showing where seismic waves go slow. And what Megan did is she put these cross sections right here, and then overlaid so this would be the predicted velocities based on things that are cold and dense, like the Bandit Terrain here, and things that aren't, like the Australian continental margin material. And you can see here that that the Australian margin just keeps going down. It doesn't, there's no slab detachment. You can see the forearc here really well, okay? But something also happens to the forearc. By the time you get up here, it doesn't go underneath, it doesn't wedge into the continent. It's gone somewhere else. And we think it's been subducted. We think that because we've done some gravity modeling, and the gravity shows that there's no forearc basement, or there's no evidence from the gravity field that the Australian basement has been involved in the folding and thrusting here, that it's the cover rocks, most of them have been sheared off of it, but the Australian basement has also gone down. There's also evidence from the volcanic arc being contaminated by those Australian margin units, which means they went down to at least 100 kilometers. But when you look at how much shortening that there's been, you look at all the shortening that you can see in these volcanic or in these accreted rocks, which means the Australian margin has to have at least gone down 300 to 400 kilometers, which means it's subducted. There's no evidence that there's been a slab tear and a plate reorganization and a polarity reversal like these initial models. And there's, in fact, no evidence of that in most other places in the world. There's maybe one example of a polarity reversal that happened in the collision of the Ontong Java Plateau with the Solomons, but not here. In the Himalaya, the Indian continental margin has gone down underneath Asia for more than 300 kilometers. So these continental margins are not pushed, they're pulled. They're pulled by the negative buoyancy of two things. First of all, the original negative buoyancy of the oceanic lithosphere, especially if it's really old and cold, like the Indian Ocean plate is, right? And the second thing is, as that oceanic plate starts to go down, we know that it turns into eclogite, which is more dense than it was before. And so it actually changes its density as it goes down. And we think the same thing happens to the Australian continental margin. It is metamorphosed by high pressure, low temperature metamorphism, and even eclogite, and even turns into, in cases, diamonds. And so the Australian continental margin, this is something that I don't think a lot of people appreciate, but continental margins, passive margins, when they reach the subduction zone, they can change into something that's subductible. They don't stay buoyant. They increase in density, and that can allow them to continue to go down. And because it's slab pull, it's difficult to have the reversal of a subduction. Some people think that this thrust right here, okay, we call it the Wetar thrust, is the initiation of reversal of subduction. But I think it's just a back arc fold and thrust belt. So it doesn't have to be a reversal. There's obviously little evidence that it's subducted far enough to create a volcanic arc, and that's because it's probably going to hit this subducting plate here. So let me just transition really quickly to this presentation, where I just want to mention that one of the most important things we can do as geoscientists is reach out. Here I am with my students. Let's see, where's my Indonesian student here, my student from the US, from the US here, and we are uncovering a tsunami deposit. You can see here that this is soil, which is covered by sand, and in that sand are shells, which came, so it's a marine sand, it wasn't a fluvial sand. This is in Ambon. And these kids are like wondering what's going on. And so I asked them where this sand came from, and they said that it came from the ocean. I said, well, when was the last time the ocean was right up here? Have you guys ever seen the ocean come here? And no. So what happened? Well, maybe there was just a really high tide, and they were right. There was a really high, people used to call these tidal waves, but now we call them tsunamis. And their village is between this and the ocean. It's over here. And so we had an opportunity to bridge a gap. Before we got there, there was this gap. These kids didn't know what a tsunami is, and they also didn't know their village was at risk. And by involving them in our research and asking them to help us find more of these and help us to make maps of them, allowed them to be empowered. We also were able to ask them what would be the best strategy for them to avoid being casualties from the tsunami. And they said, well, we'd have to have somebody constantly watching the ocean. And I said, well, that's not going to work. You guys probably sleep at night, right? What if it happens at night? And they said, well, we'd be willing to have somebody watch the ocean all the time. And I go, well, there's a better way, because tsunamis have a warning system associated with them, since most of them are generated by earthquakes. Even if they're landslide tsunamis, a lot of times the earthquake will be the first warning. As soon as you feel the ground shake, and I ask them, you guys feel excuse me, do you guys feel earthquakes? They go, yeah, we feel them all the time. And you do. If you want to feel an earthquake, go here. I go, how long do do they last? They say, oh, just a few seconds, you know, and then they're gone. I go, have you ever felt one that's longer than 20 seconds? They're like, no. So that's when you got to worry. If you feel, it's not how intense the earthquake is, it's how long it lasts. It's essentially the rupture speed. When an earthquake occurs, you know, it ruptures at a rate of 3 to 5 kilometers per second. And if you get a rupture that's 100 kilometers long, that's close to magnitude 7, which could create an earthquake. So that's 20 seconds. And so now they're empowered. When they feel an earthquake, they start to count, right? If it's getting close to 20 seconds, then they know that the earthquake has probably created a tsunami, which could be arriving in 20 minutes. So we have 20 seconds, 20 minutes, and they need to get higher than where this tsunami deposit obviously reached. This is about 10 meters high, and they need to get up to about 20 meters high. So we have this 20-20-20 rule, which let me just quickly, whoops, go there. Whoops, right here. So I want to just finish by talking about this flow diagram here. If there's a tsunami along the Java Trench or along the Timor Trough or the Tanimbar Trough or the Sram Trough, or the Wetar Thrust or the other back thrusts or any of the major plate boundaries in eastern Indonesia, right? It can cause a risk. And most of the geosciences has been focused on this part of the disaster mitigation, which is the technical part, trying to determine who's most at risk, right? And we do that by looking at historical accounts, trying to determine what areas have experienced tsunamis in the past and where those source regions were. We can look at the geologic record like we were in Ambon. We saw that tsunami deposit. We can look at areas where there's huge seismic gaps like the entire Java Trench, the Timor Trough, Tanimbar Trough, and Sram Trough. Each of these have had earthquakes in the past. Some of them megathrust earthquakes that we can reconstruct from historical accounts, but not recently. We can also do tsunami modeling, which is we use a forward model. We rupture the earth in a place where we think there's a potential seismic source area, and we can model how fast the waves go and how far they inundate the land. And we can use those to try to determine who's most at risk, right? But how much did this right here help anybody in the 2004 Sumatra tsunami? It's important to take a pause there. Almost 300,000 lives were lost. And this did not help that, did not diminish that, did not mitigate that one bit. These were in place. In fact, I published a paper in 2002 using historical accounts, using seismic gaps. I hadn't done any modeling, but showing that there was a huge risk in northern Sumatra, actually throughout the entire Sumatra area. But guess who never read that paper? The people who were in harm's way, right? So this is where most of us don't like to be. Most geologists don't like to be in the social sciences, but we have to bridge this gap between the two. Just like I was bridging that gap between those kids who didn't know anything about this by communicating. We need effective communication, and even more important, we need effective implementation of disaster mitigation strategies that work. What we've done in this area has helped us so much. For example, we do surveys where we go into an area, and just like I was talking to those kids, you know, how did the sand get here, and so on. by doing capacity surveys, we understand what the local people's capacity is for what their knowledge of tsunamis are, and if they understand what to do about it, how they can protect themselves. It's a measure of efficacy. And then we talk about natural warnings, because even though Indonesia has a tsunami warning system, it doesn't have a very good history of working to warn anyone that a tsunami is approaching. And that's because of how close the built environment is in Indonesia to the actual source of the tsunamis. The tsunami is going at 600 kilometers per hour towards the shore, but the shoreline is only 200 to 300 kilometers. I mean, the trench is only 230 kilometers offshore. So even the best tsunami warning systems are not going to be able to do anything about that. So you have to use the earthquake as the natural warning, and not the intensity of the earthquake, the length of time it shakes. So that's the first 20 here, 20 seconds of shaking. Even if it's very gentle, you have to then think about a tsunami. And you have to think about how you evacuate. So you have 20 minutes to evacuate. Now, in most places where we've been, that's not an easy task. If there's mountains very close to the shoreline, that's not a problem. But you have to get to 20 meters elevation. And so some of these coastal plains don't have 20 meters within reach in 20 seconds. And so in those cases, you have to come up with other plans, like vertical evacuation sites, or using buildings that are already there that can provide vertical evacuation, which is what saved a lot of people from the 2011 Japan tsunami. And then to evaluate the effectiveness of these, if any of this would have been in place in 2004 in Sumatra, thousands, tens of thousands of lives would have been saved. Even if the people would have just known 2020. Think of all the lives that were saved. Most people did not have any clue. I'd say probably all the people did not have any clue that a tsunami was coming. So they didn't do anything except for try to recover from 8 to 9 minutes of shaking nonstop. And then all of a sudden, here comes this wave. And by the time you see the tsunami, it's too late. It's coming in so fast, there's no way you're going to be able to get it. You have to act before you see the tsunami, which is what the 2020 is. So I'll stop there and open it for questions.
Okay, thank you for your presentations. We have some questions from the Q&A section. We have Mas Widi Hartono. Maybe Ghazali can help him to move to the panelists, and I'll start Kituron. Ghazali? Okay, Maswidi is on the panelists. Hello, Maswidi. You can unmute. There you go. We cannot hear you.
Can you hear anything, honey?
No. Maybe I can ask the question on behalf of.
Yeah, you could also have them type the question into the chat box.
Right. He did type it. So his question is, which part of the Bandit Arc that has more potential reserves for hydrocarbons? What about Timor area?
Okay. Let's go to this right here. So is my screen still shared?
Yes.
Yes.
Okay. Okay, so here's a seismic line right here. Let me see if I can find my pointer. There it is. These, as you know, these passive margin sediments, especially the pre-rift sediments on the Australian margin, are rich in hydrocarbons, especially in gas and in oil. When they go down underneath the accretionary wedge, they create oil seeps. So there is oil that's seeping out of these. The big challenge in trying to explore for oil and gas in Timor is that you have to find a reservoir which is not leaking. And as you can see, all of these faults that develop in the accretionary wedge create a challenge for large hydrocarbon reserves. But the best place to look for them is to drill through the accretionary wedge into the underlying units, especially if they haven't completely been accreted yet, and find them there, because the rocks in Timor have the correct thermal maturity for hydrocarbons, especially in the passive margin sequence, that aren't mature in on the Australian margin, but once they go down a little ways into the trench, become mature. And so I think there exists traps, and I also think we have enough reservoir rocks. We definitely have enough source rocks. The Wailulu Formation, which I mentioned, is a great source rock. We also have source rocks in the Triassic and in the Permian. And so you have all of the elements there. There just hasn't been a very aggressive exploration effort on the Indonesian side. And I don't know if the Indonesians have been scared away by the fact that it's a complex play, but there have been test wells that have been drilled on the southern coast of Timor, which is essentially be drilling through here like this, and they found these units underneath the accretionary wedge. They saw all these passive margin sequences accreted, but then they got down into here, and there were some oil shows as part of the work done by Amices. I actually consulted for them during that process, and our structural models were used to help them site the wells. So I think that there's a lot of potential. It's risky, but there's a lot of potential.
Okay, I hope that answered the question from Pak Widi. For the next question, we have Pak John from Ambon. I think to sum up his question, what would be the differences of the form of the land compared to the shaking of the earthquake?
You mean, can you look at landforms and be able to tell that this is a place that has lots of earthquakes?
Maybe, or also maybe something like something related to the fastest of the waves travels on different landform.
Well, okay. So yeah, for the last year, the Waves Consortium worked on trying to determine which areas in Eastern Indonesia are most susceptible to amplification of earthquake waves. As you know, not every place is affected the same by an earthquake. Places that are built close to bedrock, the earthquake wave will go through fairly fast and there's very little amplification. Whereas most places are built in alluvial fans, which means that they're built on unconsolidated sediment. And so what happens there is the earthquake wave, as it goes through, it slows down. And so that causes amplification of the wave, which makes the hazard of the earthquake much worse. And so we had a very interesting experience because we had done some work in Lombok back in 2018. And then after our work, they had those earthquakes. And so we went back in 2019 and we compared the damage from the earthquakes with what we call the velocity of the seismic wave in the upper 30 meters. Because that's going to determine how the built environment above that actually responds to the seismic wave. And we found that the areas like we predicted that had the most damage also had a very low VS30 number. The VS30 is just the velocity of the seismic wave. So we're talking about 200 to 300 meters per second, which is not very fast. Most seismic wave most seismic waves go faster than that. And in those places like that were built closer to the volcano, closer to bedrock and not in the alluvial basins, didn't experience as much damage. So we also did the same thing at Ambon. We went there and we did VS30 measurements throughout Ambon and Bandit and other places that have been flattened in the past. I mean, historical accounts of earthquakes in Ambon and Bandit have shown that those cities have been destroyed several times by earthquakes. And it's because when the earthquake is over and they build back the same way they built before, and not thinking that it's a recurrent process. And so now we have VS30 maps of Ambon. And then after we did the VS30 measurements, there was an earthquake in Ambon. And so if anybody's to blame for those earthquakes, it's us. We're very sorry that we did those VS30 measurements because we think by pounding on the earth with that hammer that we used, we might have activated something, but I know that's not true. And so we now have a very good feel for places where we can show are the most susceptible to earthquake damage. And these maps that we're making will help with zoning laws as long as the zoning laws are enforced, and will reduce the amount of casualties from strong earthquakes in Indonesia in the future.
Okay, thank you for the question, for the answer. I hope that answer Pak John from Ambon's question. We also have Pak Joko Wahyudiono. Pak Joko, would you like to ask your question directed to Ron? So Pak Joko's question is, do you have any evidence between the difference of melange in northern part and southern part of Timor Island?
Great question. The melange in the northern part of Timor has maybe a few more elements of the pre-rift units of the Australian margin, whereas the melange in the southern part has some of the material from the post-rift sequence. The blocks in the melange are also a little bit different, but not enough of a difference for us to actually map different facies. So we did block counts and we did XRD analysis of the matrix, and the melange in the northern part of Timor has more illite, and the Melange in the southern part of Timor has more smectite. But that's about the only difference that we found.
Okay, the next question is from Pak Supartoyo. Pak Supartoyo is from Geological Agency of Indonesia. So we have moved you to the panelists. Pak, if you would like to ask your question directly to Ron, you're able to do that. Oh, he said that his signal is unstable. So his first question is, when did the Fluoresce back arc thrust was formed?
Ooh, great question. Let me go to this right here. Okay, so I think that the formation of the Fluoresce back arc thrust happened at 4 million years ago. You can see here that I show the volcanic arc in gray, and there's no displacement along it at all. Then what happens is you first start to shorten. You can see that the width of the continental margin here gets less and less and less. And that's just showing that that is shortened. And so that's why you get uplift. And I think when 4 million years ago, you had the indentation of the arc, that's what started to shut down or started the Wetar thrust. Although the island of Wetar continued to be active volcanically, just like the Fluoresce arc is still active, even though the Fluoresce thrust is there, right? And then by 2 million years, I think you started to offset it, and this offset in the last 2 million years, you can see here. So we call that a back arc thrust, but the thrust that was behind Sumba and behind Savu and on the north coast of Timor, we think has been active during the entire collision and still is active. And so there's two back thrusts. There's a back thrust right here, and there's a back thrust on the other side of the arc. And this back thrust is allowing for the orogenic wedge to move over the forearc, and this back thrust here is allowing the arc to move over the back arc.
Okay. His second question is also a good one. So what is the best mitigation effort if the source of the tsunami is near from the coast and the time was limited, such as tsunami in Palu 2018 and Sunda Strait in 2019?
Okay, so those two tsunamis, I agree with you. Those, especially the one in the Sunda Strait, where Krakatoa collapsed. The only way anybody could have been warned of that is to actually have Anak Krakatoa monitored. It amazes me that as dangerous as that volcano is, and how much havoc it has wreaked in the Sunda Strait, that there's not a better monitoring system. I know it's problematic because seismometers and other types of instruments that you could put there are commonly destroyed by the volcano. But that's the only way we could have done anything with the problem in the Sunda Strait. And even if we would have been able to see that the landslide occurred somehow or monitor it somehow, there still would not have been time to warn the people that were on the coast. because we don't have a mechanism for warning them, a good mechanism for warning them. So we have to accept our losses in those cases where there's landslide tsunamis. In Palu, even though there were landslide tsunamis that occurred just minutes after the earthquake, the inundation in Palu was not that great. It didn't go very far inland. And so if people would have known that the earthquake was the warning for a possible tsunami, there would have been a lot less deaths in Palu. I visited Palu and I saw the damage and I talked to the people. And even though there's been lots of tsunamis around Indonesia, still the people in Palu, because of how horrific the earthquake is, right? It's very difficult to know what to do next and to start to prepare for a tsunami. Some of the people in Palu actually knew they had to run because a tsunami might be coming, which was great. But the majority of them didn't know that. And that's something that has to be taken care of by better education. And none of the people in Palu that I talked to had ever done an evacuation drill. Now that's just wrong. If you live in a place like Palu, right next to the ocean, right on an active fault, you should do evacuation drills in schools, at least, right? And have community evacuation drills. That's also the case in most of the places in Indonesia that I have visited that are at high tsunami risk. There's no evacuation drills. The evacuation drill is the most important thing you could possibly do in those areas to prepare the people for when it happens.
Okay, thank you for the answer. We have two last question from two different people. The first one is from Ifkar Haki. Is there any similar mechanism or processes that happen in Timor as well as in Bhutan Island?
Unfortunately, I am not the best person to ask about Bhutan. There's a lot more strike slip tectonics in Bhutan than there is in Timor, but I have not done field work in Bhutan. My knowledge of Bhutan only comes from publications, and there's not very many. So in one sense, Bhutan can be compared to Ambon and Seram in the fact that there are pieces of the Northern Australian margin that are cut up in the collision zone. But that's as far as I know as the comparisons can go.
Okay, thank you.
So I am open. If you want more information on Bhutan, I would love to go there if you want to take me there and be my host.
Okay, our last question is from Mas Angga. I would like Mas Angga to ask directly to Dr. Harris. I know Mas Angga from You Inspire. He is a very great Earth storyteller. If you guys check out his Instagram, it is very digestible and also very popular geology type of writing. Mas Angga, would you like to ask your question directly to Dr. Harris? We cannot hear you. Okay, so his question is, I'd like to ask about Savo Island. We found Middle Jurassic radiolaria in Wailulu Shale directly above the Padaro Sandstone, which is dated as Triassic age by your research. My question is it possible if Padaro Sandstone have younger age than Triassic or early Triassic maybe?
Yes, it's very possible. We only did our correlation based on lithostratigraphy. We didn't have any biostratigraphy of our own from Savu. And so, yes, it's very possible that the age could be Jurassic. Does he have any fossil information from the Padaro sandstone?
He said that he found a Middle Jurassic radiolaria directly above Padaro sandstone.
Right, but within the Padaro itself, we couldn't find very many fossils.
Right, I think he has the same problem. That's why his reference is the fossil above it.
Yeah. Yeah, has he published those ages?
If you publish the ages, Masanga, you can type it on the chat. Oh, he hasn't.
Okay.
Okay. So yeah, we are 30 minutes late. So I think that's the last question. I think we gave you a lot more time for your talk compared to when you're here and invited by the local governments or the universities here.
Yeah, we should do this some more. I mean, I only got halfway through the Timor story. We didn't talk about the geology in East Timor or the metamorphic rocks or the evidence for and against slab tear or continental subduction. We didn't talk about volcanic arc very much. So yeah, I'd be willing to do a Bandit arc too if you guys want to.
Yeah, so we might have a sequel of Bandit arc too.
Okay, excellent. And we could also have a meeting. We could also have a talk just on the disaster mitigation.
Right, because it was a small portion on this webinar about it was only a small portion of the webinar that you talk about the hazard and mitigation.
Yeah.
But yeah, we get the general idea, and we would like to thank you again for your time. You woke up super early for this webinar, and I would also like to thank all the participants. And don't forget to check out the ice mine at www.icemine.upnyk.ac.id. If you write something within or like in line with the themes that this international seminars, you can submit it there, and we will have a virtual seminar on November 25th. Thank you. That's all from me. Papras, would you like to say something to close this?
Yeah, just say again thanks to terima kasih banyak untuk Prof Harris. Ron, thank you very much for your kindness to share your invaluable experience in Timor to us.
My pleasure.
Yeah, that's all. Hanif, and selamat siang ya, Ron.
Ya.
Selamat siang.
Masih pagi.
Ya, masih pagi. Di sini sudah malam. Sudah ya.
9.
Okay. Selamat malam.
Selamat malam.
Selamat tidur.
Terima kasih semuanya.
Good to see you, Hanif.
See you. Good to see you too.
We need to publish your results. What do you want to do about that?
I would like to publish it.
Ron, there is Julian. Say hello in chat.
Oh, Julian. Where is she? Is she on there?
Ya. Mas Ghazali, tolong dipanelkan Mbak Julian.
Freta Julian, Gus. Okay.
Oh, there she is.
Yeah.
She's muted though.
Yeah.
There she is.
Ah,
Hi, Julian.
Speaker. Di unmute. Itu dia.
Oh, there she is. Okay.
Yeah.
Okay.
Selamat malam.
Ya, di sini sudah malam. So it's
11 o'clock.
11. Yeah. But I'm so excited because I can meet you in this webinar, and I hope that maybe next part you will talk about disaster mitigation.
Yes. If you get me started talking about band architectonics, it's really hard to stop.
Yep.
And so we need to have a webinar just for disaster mitigation.
Yeah.
And we'll start with the disaster mitigation and not talk about the tectonics as much.
Yeah.
Yeah.